So let's use those reactions that we just learned, those 6 different steps. And now we're going to add a chlorine to methane. So chlorination of methane, we start here with methane, we add chlorine, and have to add some energy and add it in the form of light, and we're going to make a methyl chloride. The reaction is initiated by the homolytic cleavage of chlorine. So we start with chlorine, and we're going to put 1 electron on this side, and the other electron is going to go on that side, and we'll get 2 free radicals. The propagation step involves a hydrogen extraction. So we're going to break the bond between the carbon and the hydrogen, and we're going to make a bond between the chlorine and the hydrogen. So one of these electrons in the bond between the carbon and the hydrogen is going to go back to the carbon. The other electron is going to form part of a new bond, and the electron attached to the chlorine is also going to be involved in that new bond. So our new molecule, we've got a radical here, and hydrogen chloride. So you might guess that our radical here is not going to be very stable, and it's going to react with a chloride molecule. And so one of these electrons attaching the chlorine to the chlorine is going to go and live on the chlorine. The other is going to form a new bond. And this electron that's by itself is also going to be part of that new bond. So now we're making a bond between the carbon and the chlorine and a chloride free radical. This is a chain reaction because our chloride free radical can go on to recruit another methane molecule, so that one of the chloride radicals can result in thousands of molecules. It's worth looking at, if we add the 2 propagation steps together, we will get the net reaction. So the methane plus a chloride radical and will end up giving us methane radical and hydrochloric acid, and then the methane radical and chloride gives us our product. So let's draw the mechanism for the radical chlorination of methyl chloride to produce methylene chloride. So we're just going to add another chloride. I'd like you to stop the tape and try and do this on your own. Okay, so I hope you've had a go at it. The initial step is, of course, going to be making the radical to start with. Draw the line. So let's make them pink. Why not? So one electron goes this way, the other electron goes that way. Propagation step. Going to sorry, my writing's not the best. So we need to break this bond here, and so one of the electrons is going to go back to that carbon, and the other electron is going to make this new bond, and this is the other half of that new bond. We've got 3 arrows. The next step in propagation is that of a halogen extraction. So we've got and that's a free radical, and it's going to interact with a chloride molecule, and we're going to make our final product. So up to this double bond here, one of these electrons is going to go that way, and the other is going to make a new bond. There's the other half of that new bond, and there's the new bond. And we've also regenerated our chlorine radical so we can go on and complete the process again. So our directions ask us here to draw one termination step. Termination step is any time two free radicals come together. So let's say we've got this free radical, and instead of meeting a chloride molecule, it meets a chloride radical. And what will happen here is these two guys will get together, they'll make a bond, and we'll get and this is our product, it's the same product, but no radical is made. So it doesn't propagate. So that's why we call it a termination step. Now there are a couple ways that we can favor this process. The homolytic cleavage requires energy, and we've been showing this as UV. It can also be heat. At a temperature of about 300 degrees, which is going to cook most of our organic molecules, right? So we have initiators that we can add to lower the energy requirements to about 80 degrees C. And this is a popular one because it is resonance stabilized. The radical can either go here, or it can go over here. Also, this is why we saw the peroxides. So any of the peroxides will help initiate this process because it stabilizes the radicals. We can stop this reaction using a radical scavenger. This destroys radicals and prevents the chain process. And for example, if we've got molecular oxygen, each oxygen can destroy two radicals. And hydroquinone also is a very good inhibitor because it has a radical here, but it's resonance stabilized, and so it doesn't react as easily. The second hydrogen extraction destroys another radical. So we can do each molecule of hydroquinone can get rid of two radicals, and then the hydroquinone becomes benzoquinone. And so the radicals are completely destroyed.